All right, let's dive into what is, no joke, the single biggest change in radio technology in the last 50 years. It's a revolution that's happening deep inside the electronics, and believe me, it is completely changing what's possible.
So here's the big idea. For decades, we've had all this complicated analog stuff in our radios. We're now at a point where we can just get rid of it. We're going straight from the radio waves in the air, the RF signal, directly to ones and zeros. This is a huge leap. But to really get why this is such a game changer, we got to first look back at the incredibly complex problem it's solving.
For the better part of a century, building a radio receiver was like designing this intricate analog labyrinth. A signal would come in from the antenna, and it had to navigate this whole maze of different components before we could get anything useful out of it.
And for most of that time, one design really ruled them all, the super heterodyning. Super clever, but also super complex. Then around the 2000s, things got a bit simpler with something called direct conversion, or zero IF. But now both of those old-school analog ways are giving way to something totally different, direct RF sampling.
So what exactly was this old way? Well, just imagine you've got this super high-frequency signal coming in from the antenna. You can't just process it like that, it's way too fast. You have to bring it down to a more manageable frequency. And you couldn't do it in one big jump. Nope. You had to do it gradually, stepping it down through a whole chain of different analog parts.
And this was your toolkit. You needed mixers to do the frequency shifting, local oscillators to give them a signal to mix with, complex synthesizers to even create those signals, and that's before you get to all the special amplifiers and filters you needed at each stage. All of this hardware, it added size, it cost a lot of money, and man, it ate up a ton of power. It was really a marvel of analog engineering for sure, but it was also a massive bottleneck.
And that brings us to the revolution. The elegant, almost beautiful solution that just throws that entire analog labyrinth right out the window for something radically simpler.
So, what made it all possible? This number right here. The secret sauce is the absolutely mind-blowing speed of modern analog to digital converters, or ADCs. We are talking about little chips that can take snapshots, or samples of a radio wave over 20 billion times a second. That kind of speed makes what was once impossible, well, suddenly possible.
And this picture just says it all, doesn't it? The new way is just RF to bits. That entire chain we just talked about, the mixers, the oscillators, all those filters, it all gets replaced by one single, insanely fast chip. The hardware complexity just evaporates.
But hang on a second. If you know a little bit about signal processing, this might be setting off some serious alarm bells in your head right now. How in the world can this actually work? This feels like it breaks one of the fundamental laws of digital signals.
I mean, here's the million-dollar question, right? Let's say you've got a 28 gigahertz 5G signal. Today's fancy ADCs can sample at maybe 12.8 gigasamples per second. So how can you possibly capture a 28 gigahertz signal by sampling it at less than half its frequency? Doesn't this just completely shatter the famous Nyquist theorem?
Well, this is where we have to read the fine print. Let's look really closely at what the Nyquist theorem actually says. It states that you have to sample at a rate that's at least twice the signal's bandwidth. And that one word, bandwidth, is the key to this whole magic trick.
See, here's the secret. The rule isn't about the super high carrier frequency that the signal is riding on. It's about the width of the actual information you're trying to capture. So a 5G signal might live way up at 28 gigahertz, but the chunk of information it's carrying might only be a few hundred megahertz wide. As long as your sampling rate is more than twice that width, you're totally fine.
So how does this work? The best way to think about it is to imagine the entire radio spectrum is a long strip of paper. Your 28 gigahertz signal is way down at the end. Now the sampling process is like folding that paper in half, over and over again. Your signal, which is way out there in a high Nyquist zone, gets folded down or aliased into the very first section of the paper. And just like that, your 28 gigahertz signal, after being sampled at 12.8 gigasamples per second, magically shows up as a perfectly clean digital signal at 2.4 gigahertz. And you did it all without a single analog mixer. It's incredible.
But you know how it is in engineering. There is never, ever a free lunch. We didn't actually eliminate complexity. We just moved it. It's now taken on a new, and sometimes spooky, digital form.
It's like Dr. Mohammad Nizami said, we totally cleaned up the analog chain, which is great, but what we really did was push all that complexity into the ADC itself and all the digital processing that has to happen after it. We've traded one set of problems for another.
And these new problems have a name. We call them spurs. They're like little digital ghosts or artifacts that pop up where you don't want them. You get harmonics, which are unwanted copies of your signal. You get something called interleaver spurs, which are caused by tiny little mismatches between all the different cores inside the ADC working together. And you get clock spurs from any tiny imperfection in that super fast sampling clock. Any of these can land right on top of your signal and completely ruin it.
So, how do you fight these digital ghosts? Well, funny enough, the solution looks a lot like what engineers used to do in the old analog days. It all comes down to careful planning.
We call it digital frequency planning. So instead of worrying about where an analog mixer's unwanted garbage is going to land, engineers now have to meticulously, painstakingly choose the perfect sampling frequency for the ADC. The whole goal is to make sure all those nasty spurs, the harmonics, the aliases, all fold down into harmless locations, leaving a perfectly clean window for the real signal we actually care about.
And this is the result. Look at the left, a poorly chosen sample rate, and bam, you've got digital spurs landing right on top of your signal. It's a mess. But on the right, with a well-planned frequency, you've cleverly moved all those red spurs out of the way, and your blue signal is sitting there clean and clear. It really is like a chess game, but played across the entire frequency spectrum.
So, why do we go through all this trouble? Why does this matter? Because getting this right unlocks a future where our radios are more powerful and way more flexible than we ever could have imagined.
Direct RF sampling is the engine that makes true software-defined radio possible. We're talking about one single piece of hardware that can be your 5G phone 1 minute and a GPS receiver the next, just by changing the software. This is absolutely critical for 5G, for the 6G networks of the future, for advanced radars, for satellite communications, the list goes on. And of course, by getting rid of all that extra analog hardware, it leads to smaller, cheaper, and more power-efficient devices for all of us.
At the end of the day, this revolution is about so much more than a clever engineering trick. It fundamentally changes the entire relationship between hardware and software. So it leaves us with one final big question. When a radio is no longer defined by a fixed piece of hardware, but by lines of code, what becomes possible? What are we going to build next?